This active fault suddenly appeared in Awaji City in Hyogo Prefecture after a major earthquake 18 years ago. About 10 kilometers of the fault can be seen above ground. But the fault was actually far longer, stretching more than 40 kilometers underground. When it shifted, it devastated the city. It was a near-field earthquake, in which huge vibrations caused by the active fault strike from below. 4 tectonic plates surround Japan. The plates push against each other, fracturing the earth. These fractures are the active faults that cause earthquakes. Japan has become more seismically active since the Great East Japan earthquake on March 11, 2011. Scientists are now particularly concerned about near-field earthquakes caused by active faults.
Active faults often caused large earthquakes in inland areas after a major earthquake occurs.
Around 2,000 active faults have been found in Japan so far. Now, previously undiscovered faults are becoming active.
I only found out there was an active fault here when it caused some damage.
It's just terrifying. A quake could strike in a second, and there's nothing we can do.
MEGAQUAKE. We still don't know the true threat posed by the active faults that lie beneath our feet. Where will the next near-field quake strike? Scientists are trying to get an accurate picture of the active faults hidden underground. One such fault passes directly underneath Tokyo. If it were to slip, it would likely cause tremendous damage to much of the Tokyo metropolitan area. In Osaka, the latest technology has finally revealed a long-hidden fault. What does this massive fault look like? It is split into many branches, making it likely to cause considerable damage.
The faults spread out over wide areas. They create the energy and waves that cause earthquakes. I think we need to work on seeing how far they extend underground.
The MEGAQUAKE series will try to unravel the mystery of earthquakes using the latest technology. The first program will focus on the growing threat at our feet and uncover the true nature of active faults. A month after the disaster on March 11th, a magnitude 7 earthquake hit Fukushima Prefecture. The epicenter was directly under Iwaki City. Unlike the major earthquake off the coast of the Tohoku region, this was a near-field earthquake that occurred inland. Part of a mountain crumbled in the massive quake. 4 people died, including a high school student. This quake was caused by an active fault hidden underground. The active fault suddenly appeared in this temple in Iwaki City.
This is where the fault is running. It just suddenly appeared and cut right through our land.
The main hall of this temple became tilted. It now leans to one side. A fault ran underneath the building, and the ground had collapsed on one side of it. The active fault that ran through the temple grounds was 13 kilometers long. Two active faults appeared above ground during this earthquake. In some places, the ground fell as much as 2 meters. Why did such a major slip appear? Professor Shinji Toda of Tohoku University studied the site.
The cause lies beneath the ground. This fault continues deeper, down around 10 kilometers. I think that deeper part of the fault was to blame.
Toda attempted to probe the nature of the faults that caused the earthquake. The yellow lines show the two active faults that appeared above ground. If we add the epicenters of the major earthquake and the aftershocks, we see two distinct sides. These are the earthquake source faults, which caused the huge earthquake. The two sides slipped together, sending up strong vibrations. The earthquake source faults can be found in the hard rock in the underground portion of active faults. The surrounding areas press in on the layer of solid rock, creating stress. When the pressure becomes too great, the source fault slips, fracturing the surface and creating strong quakes. This time, two source faults, 15 kilometers wide and 10 kilometers deep, shifted significantly, causing active faults to rise to the surface. Toda learned something surprising while studying this earthquake. Before the catastrophic earthquake 2 years ago, the oceanic plate pushed against the Tohoku region, and the inland areas were under great stress. The earthquake source fault underground was also being pushed. As pressure built up there, it became likelier that an earthquake would occur. The 2008 Iwate-Miyagi Nairiku earthquake happened this way. It killed 17 people. Then, when a major earthquake struck in 2011, the built-up pressure was released. Toda thought that would lower the risk of the active fault causing another quake. But soon after, an earthquake hit Iwaki City.
Our calculations indicated that the stress on the inland areas of the Tohoku region had been reduced, so there shouldn't have been a quake. But there were some areas inland where seismic activity occurred frequently. For a while, I didn't understand why that was happening.
Why were there earthquakes in such an unlikely area? Toda took a closer look at the way the active fault slipped. The fault was pulled from the eastern side, and the ground on the western side collapsed. Toda identified a new characteristic of earthquakes. After that major earthquake, the movement of the continental plate was pulled into the opposite of its former direction. The same happened to the earthquake source fault. Because the direction of the force was reversed, it became easier for an earthquake to occur at the active fault. In the past 2 years, Japan has been pulled eastward by as much as 6 meters. Toda says it's possible that similar types of earthquakes will happen more frequently.
The fault is moving like it's being pulled, which is something we hadn't predicted. We need to continue to look at the dangers of earthquakes and active faults.
Earthquakes that are thought to have been caused by active faults are happening all over. These quakes have registered above 5 lower on the Japanese scale in the last 2 years. They are occurring frequently in areas other than the epicenter of the major quake in the Pacific Ocean. 3 people died in the earthquake which shook the northern area of Nagano Prefecture in March 2 years ago. Another earthquake hit the eastern part of Shizuoka Prefecture, directly under Mount Fuji. And in February of this year, a quake struck the northern part of Tochigi Prefecture. All of these quakes occurred far from the epicenter of the March 11th earthquake. What was happening underground? Takuya Nishimura analyzes the movements of the Earth's crust all over Japan. He studied data from GPS monitoring stations in various parts of Japan. He noticed something strange that had not been recorded previously.
I've never seen upheavals of this pattern on this scale before.
The ground had been pushed up in regions at a certain distance from the epicenter. The affected areas were concentrated in regions including Kanto Koshinetsu and Hokkaido. They formed a circle focused on the epicenter, about 400 kilometers away. The places where large quakes had occurred and the regions where the ground had risen matched almost perfectly.
Because the crustal movements are different than usual, the force that's applied to the fault changes. It becomes likelier that an earthquake will happen there.
This is what Nishimura believes is the relationship between earthquakes and the upheavals on the surface. The March 11th earthquake happened where two plates meet. Under the epicenter lay the mantle, a layer of soft substance beneath the surface of the Earth. During the earthquake, the mantle also changed. As the continental plate moved eastward, the mantle was pulled in the same direction. The sudden movement caused a portion of the mantle to move upward. It pushed up the ground in areas 400 kilometers from the epicenter. Nishimura thinks that it was easier for the active fault to move because it was pushed up from below at the same time as it was pulled eastward. There are many active faults in places where such upheavals have been observed. Nishimura warns that these areas need to be monitored closely.
It was a massive 9.0 earthquake, so the effects will continue quite a while. These crust movements will probably continue for 10 years, maybe even several decades. People must be aware that these things will go on happening.
The Earth is covered by 12 tectonic plates. The force of their complex movements has triggered earthquakes at active faults all over the world. On the west coast of the United States, the San Andreas Fault lies on the border between the Pacific Plate and the North American Plate. In the early 20th century, part of this fault slipped, and the city of San Francisco sustained catastrophic damage. The fault is 1,300 kilometers long. Areas along the fault continue to experience tremors. Scientists now say the most dangerous area is south of the fault, near Los Angeles.
Los Angeles is right here, and the San Andreas Fault runs alongside the mountains that are just to the north of Los Angeles, because it's been over 300 years since the last major earthquake there, and on average it breaks about once every 150 years.
The Eurasian continent is being pushed by the Indo-Australian Plate. The Longmenshan Fault in China is located in the middle of the continent. In the 2008 Sichuan earthquake, a 150-kilometer-long fault slipped all at once, causing a nearby school to collapse. More than 80,000 people were killed or went missing. The Cheilongpu Fault is in Taiwan, where the Eurasian Plate and the Philippine Sea Plate push against each other. In the massive earthquake 14 years ago, an active fault rose 10 meters above the ground. And in March this year, another earthquake occurred nearby. One person died, and about 100 people were injured. A different active fault is thought to have slipped this time. Around the world, fractures in the earth slip over and over when the plates push against each other. We are at the mercy of these relentless, overwhelming forces.
Where will the next near-field earthquake happen? Scientists are carefully examining the Tachikawa Fault Zone in the Tokyo metropolitan area. The ground here has also been pushed up slightly. The zone runs between Tokyo and Saitama Prefecture and is 33 kilometers long. An active fault stretches beneath the two areas. The government estimates that a magnitude 7.3 quake could occur here. Areas along the fault could experience huge quakes registering 7 on the Japanese scale. In the worst-case scenario, 480,000 buildings would collapse or be destroyed by fire. An estimated 6,300 people would die. The Tachikawa Fault Zone is expected to cause tremendous damage, but the fault has not appeared above ground. Active faults do not always appear at the surface. Some are hidden in the sand and rocks of the sedimentary layer. The Tachikawa Fault Zone is covered by a thick layer of sediment. The location of the fault zone has been estimated by looking at places where the ground slopes gently. Studies of nearby areas have uncovered evidence of past earthquakes. Japan has begun investigating the underground portion of the Tachikawa Fault Zone, where the risk of an earthquake has increased. The zone runs through this vast land where a factory used to stand. Scientists dug a 10-meter deep trench to find signs of past active fault movement. But it's not easy to locate such traces in a layer of sediment. Researchers discovered a broken geological layer running lengthwise, but they later learned it was excavated during construction work. An active fault is lurking underground, still buried under thick sediment. An active fault often doesn't emerge until an earthquake has occurred. One town has witnessed the destructive force of an active fault and suffered huge damage. It's Christchurch, New Zealand. February 2011. A magnitude 6.3 near-field earthquake shook the town from directly below. 185 people perished, including students from Japan. The New Zealand government had released this map of active faults before the quake. Experts had located over 150. But the map didn't show any in the plain surrounding Christchurch. No active faults had been discovered in the area. The liquefied ground spewed sand and mud from the sediment layer. The earthquake had revealed that an active fault was there all along, hiding further below. Researcher Bill Fry is studying this earthquake. He had been looking for active faults below the sediment layer. It turns out the underground active fault, the source fault, was buried beneath sediment about 1 kilometer thick. Over a long period of time, a large amount of sand and mud had accumulated. It gradually concealed evidence of an active fault slip caused by an earthquake. The existence of the active fault had gone unnoticed.
In regions such as Canterbury, where you have very thick sedimentation covering the basement rocks, it's incredibly difficult to locate all of the active faults or all of the potentially active faults. That we actually had an event that we weren't expecting that caused considerable damage.
Wasn't it possible to warn people that an earthquake might occur? Fry is still hounded by regret. Actually, 6 months before the Christchurch earthquake, another massive trembler had occurred some 40 kilometers away in the same plain. Its magnitude was 7.1. That event revealed that an earthquake source fault was hiding deep underground. Fry had started investigating, suspecting there were other source faults in the area. Then, soon after, the earthquake hit Christchurch.
Before the earthquake, we could have said we believe in the deep crust or even the shallow crust, but below us, below the sedimentary material, we believe that there are faults that could happen in an earthquake. On the very basic level, we try to deliver it to the public. We try to tell the people that are being affected what we know and what we don't know. I think it's just important to tell them what we don't know as it is to tell them what we know.
The danger lying beneath layers of sediment has come to light. In Japan's Kanto Plain surrounding Tokyo, few active faults have been identified aside from the one in Tachikawa. and the area sits above a sediment layer that's thicker than the one in New Zealand. It stretches deeper the closer it gets to Tokyo Bay. The maximum depth is 5 kilometers. There could be more earthquake source faults hiding below the sedimentation. Should a source fault move, how would the tremor travel through the sediment layer? Professor Hiroaki Yamanaka of Tokyo Institute of Technology is studying how shaky the ground could become in the Kanto region. His team has set up small seismometers at 3,000 locations around the Tachikawa fault zone. Yamanaka is trying to predict the maximum possible level of tremor an earthquake could generate.
We're checking how hard the ground is because that would help us figure out how much the earth would shake in a big earthquake.
Yamanaka conducted a simulation based on data from soil around the Tachikawa fault zone. Red indicates a strong shake, and white indicates the maximum tremor. Initially, the vibration is focused near the fault, but it spreads gradually. The tremor gets especially strong in the eastern area of the fault. There's a thick sediment layer just below. The sediment is relatively soft. Yamanaka figured the thicker the layer, the more amplified the vibration would be.
To forecast the extent of tremors during an earthquake, we need to learn more about what's happening deep underground where a source fault sits, and also the soil conditions between there and the surface.
If the Tachikawa fault zone triggered an earthquake, how much damage could it cause? We did a simulation based on government estimates and various scientific investigations. An earthquake occurs on the north side of the Tachikawa fault zone. The earth shakes violently, causing massive destruction along the fault. Buildings are destroyed, as if torn apart. Cities cease to function for long periods of time. The damage and other impacts could spread beyond Tokyo into the far corners of the metropolitan area. Our society has built its cities on a foundation of invisible risks. Scientists are struggling to shed light on the threats that lurk beneath the ground. An active fault can trigger a sudden earthquake, assaulting a city from right below. Western Japan has been on high alert for the past 18 years. The port city of Kobe was devastated in 1995. A near-field earthquake took 6,434 lives. years later, another one hit western Tottori Prefecture. A quake occurred off the western coast of Fukuoka Prefecture 5 years after that. Major earthquakes have caused massive damage across western Japan. Behind these catastrophes was the Nankai Trough, a boundary between tectonic plates. It stretches west under the seabed from the south-central region of Tokai. Along the trough, stress continues to build up in the landside plate as it gets pushed by the oceanside plate. Something similar had happened off the coast of northeastern Japan before the March 11th earthquake. This makes it easier for active faults to move. Scientists are especially concerned about the Uemachi fault zone. It runs through the center of Osaka, the second largest city in the country. The active fault stretches north to south for 42 kilometers, cutting across much of the Osaka plain. But little was known about its underground structure. The yellow lines show the Uemachi fault zone. The government estimates a quake could register a maximum 7 on the Japanese scale in some areas. The worst-case death toll could reach 42,000. That would be more than double the casualties in the March 11th disaster. Isn't it possible to gain a clearer picture of the entire Uemachi fault zone? Experts began conducting research 3 years ago. The project is headed by Professor Tomotaka Iwata of Kyoto University.
Active faults are a risk, and they are hiding underground. It's very important to conduct thorough research.
Iwata's team decided to reinvestigate the area around the Uemachi fault zone using the latest equipment. Cities are covered by buildings. That makes it difficult to determine the true contours of the land. So researchers used a special laser device to capture land contours from above. Here's an aerial view of the area around Osaka Castle. The laser erases the buildings and allows the terrain to appear more clearly. The team checked the contour in detail to see if there were any active faults. Here's the result. These lines indicate the previously known Uemachi fault zone. The pink ones are possible active faults found during the investigation. They stretch to the Bay Area along the confirmed faults. How about earthquake source faults deep underground? Iwata and his colleagues analyzed the subterranean structure from above ground. They used a special device that generates vibration. They looked for hidden source faults by measuring the time it took for vibrations to return to the surface. Here's what they found. The blue part below is solid bedrock, and sitting above it is a layer of sediment. The picture shows two vertical slips in the rock. These are source faults that could trigger an earthquake.
The faults are over here, in the rock, slanting down toward the east like this.
Combining the results of the aerial land survey and underground structural data, the team has figured out the shape of the Uimachi fault zone for the first time. Here's what it looks like. The deepest part reaches 15 kilometers below the surface. It stretches north to south for over 40 kilometers. It's an enormous earthquake source fault. Furthermore, it splits into numerous branches toward the surface. They're connected to newly discovered geographical features that are suspected to be active faults. We recreated the branching process using a laboratory model. Keep pressing the ground hard, and it slips at an angle. Push further, and the rift branches off as it rises higher. The Uimachi fault lines are all connected underground. They could slide at the same time, triggering a much stronger quake than previously thought possible.
Rather than a single line or area, what we have are complicated formations that could change shape in some places. We hope that the new findings will help us better foresee what could happen and present possible scenarios for future earthquakes.
No other earthquake source faults are as clearly understood as those in the Uimachi fault zone. Using advanced technology, experts are planning to probe active faults in other areas. The people of Christchurch experienced disaster when an active fault deep underground suddenly moved. A memorial ceremony in February marked the second anniversary of the quake. A study was underway at one corner of the quake-scarred town. Scientists were working hard, trying to find earthquake source faults beneath the sediment layer.
The number of faults in an area is proportional to the number of people looking for them. So the more we are looking for these faults, the more we actually find. And so I expect that we will continue to find many of these so-called unknown faults, and that people should really expect to have earthquakes anywhere when you're located in a seismic region.
And in Japan, research has begun. that could help predict the next earthquake. This is Professor Yasuo Ogawa of Tokyo Institute of Technology. He's researching the role of underground water in earthquakes. By applying an electric current to the earth and checking variations in resistance, he examines water contained in a huge mass of rock deep underground. 2 years ago, an active fault appeared in Iwaki City, Fukushima Prefecture, some 10 kilometers below the ground. Ogawa has found a massive rock that contains large amounts of water right next to an earthquake source fault. Back then, the area experienced many small earthquakes. They were soon followed by bigger ones. Did the water make it easier for the source fault to move? Ogawa hopes to find the relationship between water and earthquakes.
We're still covering the basic ground in our research. But what we believe, that water deposits are key to understanding inland earthquakes. Eventually, we might be able to predict temblors before they actually occur.
Takuya Nishimura has been studying movements in the Earth's crust in a bid to uncover the next risk. The Japanese archipelago is still undergoing changes. Nishimura continues his analysis, trying to pick up even the smallest clue.
It's been 2 years since the March 11th earthquake. That may be a long time for humans, but it's only a short moment for the Earth. We haven't seen the end of all the phenomena. We'll need to look at tectonic movements in the islands of Japan for a long time, over the next several decades.
MEGAQUAKE. The invisible threat lurks beneath our feet. The whole mechanism remains shrouded in multiple mysteries that need to be solved. But for the sake of future generations, we must keep pursuing the threat to find out where it's hiding.